So let us now consider the operation that we just discussed, which is add R1, R2, R3, and we are going to consume this immediately R4, R1, R5, and we are going to understand how the read after write in the immediately next clock cycle is going to be consistent and correct by looking at a timing diagram of the data flow. Okay, so of course let us now just consider this register file with appropriate signals. Okay, I have a write enable here. I have a clock, of course, because this whole thing is, the write is sequential. So then I have a read address, port A. I have a read address, port B, and then I have a write address, which is again for the write port. Okay, and I am going to call the data in as D in. Okay, so let me just label this. All of these are 5-bit buses, whereas the data in is 32, and D out A and D out B, right? These are 32, 32. So this is my register file. Okay, so now what we are going to do is we are going to look at the timing diagram in order to understand how these two instructions are going to get executed one after the other. Okay, so remember, this is my destination register, this is my source register A, this is my source register B. Okay, so there are two source registers on the two read ports, one destination register for the write port. Okay, and of course the opcode that we discussed is 00 for add and 01 for subtract. So we need to just look at two cycles. Okay, so I'll draw this slightly more elongated so that we have enough time and space to discuss all the delays that we are going to incur in this process. This is my sampling edge of the clock. Okay, the flip-flops and register file will react to this. That means the write and all can happen only synchronous to this particular edge. Okay, and let me mark these boundaries. The x-axis of course is time. Okay, the x-axis is time, and basically what I want to now do is to look at what is my RA address that goes into this register file for these two operations. Okay, so if you look at this, it will take some time for you to get the signal onto RA. Now how much that time is, we will come to a little later, because there is some control block that is going to do that decoding and all that, but nevertheless. Okay, so RA is basically going to get the source address R2 here, and it is going to be R1 in the next clock cycle. Okay, that is what we are talking about here, right? Likewise, R source B will start with R3 and then shift to R5. So again, this will be very similar to this RSA that we wrote. Okay, and therefore you are going to look at R3 here and R5 here. Okay, this is my RB port on the register file. This is a 5-bit number, right? So just to remind you, this actually translates to 00010, right, and corresponding numbers for 1, 3 and 5 as well. Okay, now my W write port address in this case is going to be this R1 and R4 in the 2 clock cycles. So therefore, this again okay, so this is going to be R1 in this case and this is going to be R4. Okay, now my operation code that is going to go to the ALU, right? Remember that it is basically going to be this, right? What is the operation code? This is going to be addition, add 00 code. And this is going to be subtraction 0, 1. Okay. Now, what happens to the write enable signal? Okay, write enable is a signal that is needed in order to cause a write. Remember, this write enable goes to the enable of that decoder. So you have 5 bits of WA going into the decoder. You will get 32 outputs, but one of those 32 outputs can go high corresponding to this 5-bit input only if the write enable is high, which is connected to that enable of the decoder. And therefore, this write enable, we need to understand when the signal needs to go high. Okay, so typically we will indicate it to be like this. So for the purpose of this discussion, let us assume that I am looking at the write enable only for the first instruction, add R1, R2, R3. Write is not happening in the second, though in reality it is. Okay, so that I can discuss the timing more specifically here. So typically we are going to assume that the write is going to happen in the same cycle. Remember, so whatever we are talking about, we are actually talking about the whole thing happening within the same cycle. Okay, so now what is going to happen? We are going to basically feed this D out A and D out B will come out after some time, and that is going to go into the ALU. Okay, remember that. So let me just draw that picture here. If you look at it, if you look at this, it will be like this, right? My D out A is here. This is my operation 2-bit code which is going to decide what to do with this thing, right? And then we are going to take this output and feed it back to the D in here. This is going to go back to the D in like this, and that data needs to get written back into that particular register. In this case, it has to get written into R1 because the write address 5 bits corresponds to R1. Okay, so therefore we have enabled W enable like this and all that. So let us now look at what point and where does this data become ready to be written back into the register R1, right? So first of all, if you look at this, there is a certain delay that has happened for RA to appear at the register file. Now that delay will come to a little later, but after that has come, right, we need to understand what is the delay that is incurred in the register file to see the data out at the bus. So remember that we have the register file itself was basically register R0, R1 all the way to R31, and there is a decoder here which is a 5:32 decoder, right? So this is my RA address which is coming here, okay, and I have a multiplexer here, okay, and more specifically let me just say that this is all coming through a tri-state inverter. Right, each of these this is enable 0, enable 1, right, enable A0, let me do this, A0, enable A1, enable A31. So this is going to put out 32 signals called enable A0, enable A1 all the way to enable A31, right? And therefore, when RA appears at the input to this 5:32 decoder, the delay that is going to be incurred in getting the data from the corresponding register, right? In this case, RA is R2. So, data from R2, right? This is where R2 is, right? This path has to come out through its tri-state inverter ENA2 onto this. So, if you look at the delay here, it has to go through this 5:32 decoder and come out through the tri-state inverter, and then it will appear on the A bus. Okay, so therefore you have the A bus here, which is basically coming out to this. That's what we are calling as D out A, which is going to the A input of the ALU, right? So therefore this delay, right, in red is what I am going to call as TRF read. Okay, this delay is what I will call as TRF read. It's a register file read time, and remember, this is purely combinational in nature. It's going through a combinational block called the decoder followed by a tri-state inverter, and the data will be ready at that point. And therefore, all I have to now do is this D out A, right? Remember, this can have some contamination delay, and it can start changing as soon as some shortest path gets activated, right? But effectively, from this time here, my this is what I am calling as TRF read, right? So the data that is sitting in R2, right, will appear exactly at this D out A, okay, and therefore you are going to get contents of R2 onto this 32-bit bus. Likewise, D out B will go through a similar path, but it will happen in parallel, right? Remember, it's a very similar 5:32 decoder. It's actually the same decoder, a different instance, right? And therefore you will get contents of R3 out here. So this is my D out B, right? Now what is going to happen? You are going to get the ALU answer out here, right? So this is the time it's going to take. So after D out A and D out B come here, right? So this is basically going to be an other very similar time, and both of these are basically just TRF read. So let me just bring that back, right? So I can remove this. Yeah, so this is TRF read, okay, and both these are exactly, assuming that the paths are very similar and they are identical circuits, which is the case, right? You are going to have, assuming no manufacturing variations and all that, you can assume that these two are exactly identical delays called TRF read, okay. So after this, the ALU will take some time to finish its operation. Now how much time will that take? So the addition, the ANDing, all of these can have different times, but all we can say is the propagation delay of the ALU will be dominated by its slowest operation, which may be addition, right? Because bitwise ANDing and all happens in parallel. There is no cascading of signals there, and therefore the bitwise AND, OR and all will happen much faster compared to add, subtract and all, where the carry or the borrow has to propagate from one stage to another. Therefore, the addition operation here that we are going to do, add R1, R2, R3, is going to take a sufficiently long time, right? And what will happen? Therefore, my D in, right, in this case is basically going through back to that guy, right? And therefore, this is my D in A. Or no, it's just called D in, right? It's the data in for the right port. So as soon as my D out A and B start changing, the ALU's contamination delay will start reacting, right? It will start causing some changes, right? And it will take some time, and after the longest possible delay, it is going to come and settle to its final value. So if you look at this, this is the time. If you look at this time here, this is the earliest time at which data of R2 plus R3 is now ready and can be written back into my R1 register. Okay. So therefore, first thing is, of course, this is a sequential operation, and therefore what you need to do is, either from here, right, I will say this is what I will call as TALU, right, TALU, and from here to the clock, I want to ensure that it is setup time before the clock edge, so that data can be sampled correctly. Otherwise, if D in is changing in this period, then no way that the write operation into the register will happen correctly. Okay. So now let us look at what happens to this, how the write process happens, because D in is now ready with its data, but the write operation is sequential, unlike the read operation. Okay, that means only on the next clock edge can data get written into the register.